Welcome to Wisdom Docs. Settle in. Let your shoulders drop a little lower than they are right now. Wherever you are tonight, whatever the day asked of you, you can set it down here. The lamp is low, the water outside is still, and we are going to drift slowly together into a year that the world has spent 14 centuries trying to remember. Let me begin with a man who is long dead, who wrote something down so that you and I could read it now. His name was Procopius of Caesarea. He was a Byzantine historian, which means he lived in the eastern half of what had once been the Roman Empire, and he worked close to the powerful men of his age, watching their wars and their plagues and their politics, and writing it all into a book he called the History of the Wars. And somewhere in the fourth book of that history, in the part where he was recording a war against a people called the Vandals, Procopius set down his pen against something that was not a war at all, something he could not explain, something in the sky. He wrote that the sun had given forth its light without brightness, not gone, not absent, but somehow drained of its strength, its warmth, its ordinary fierce gold. He compared it to the moon. The sun, he said, was shining like the moon shines. Pale, cool, a disk you could almost look at without flinching, a light that fell on the fields and the rooftops and gave no real heat back to them. He said it seemed exceedingly like the sun in eclipse, and he chose his words carefully because Procopius was an educated man and he knew exactly what an eclipse was. Here is the part you have to let sit with you for a moment, because it is the whole strangeness of the thing. An eclipse lasts minutes. You have perhaps seen one yourself, or seen film of one, the way the light goes thin and silver, the way birds fall quiet thinking night has come early, the way a cold runs across your skin. And then it passes. The moon slides on. The sun returns. The whole event, from the first bite out of the disk to its full restoration, is the matter of an afternoon. It is brief enough to gather a crowd for, brief enough to remember as an event with a beginning and an end. But Procopius was not describing minutes. He wrote that the sun shone like this during the whole year. The whole year? Picture that slowly. Imagine waking and the light at your window is wrong, and it is wrong again the next morning, and the next, and you wait for it to right itself, and it does not. Imagine a spring that arrives wearing the wrong face, a summer that never quite catches fire. The sun hung there in a washed-out sky, day after day after day, giving you a light you could stare into and a warmth you could not feel. And nobody, not Procopius, not the farmers, not the emperor, not the wisest men in the libraries of the age, nobody could tell you why. He called it a most dread portent, a dreadful sign, and in his world a sign meant the gods or fate were trying to tell you something, and the message did not look kind. He wrote in that same passage that from this time forward men were free neither from war nor pestilence nor any other thing leading to death. He felt in his bones that the dimmed sun was the doorway into something terrible. And as we will see across these long, slow hours together, he was not wrong. He simply had no way of knowing how right he was or why. So here is the mystery, laid out the way you might lay out three objects on a table by lamplight before you try to understand them. The first thing we do not know, or rather the first thing the people of that age did not know, is what actually happened. What was this dimming? What hung in the air between the earth and the sun for a year and bled the warmth out of the light? Procopius could describe it. He could not name it. The second thing is when. And this seems almost too simple to be a mystery, but hold on, because it becomes the very hinge of the whole story. We will come to a year, and I will say it to you plainly, and the year 536 of the Common Era. But getting the world to agree on that exact year, getting three completely different kinds of evidence to all point a finger at the same 12 months, took a very long time and a very surprising correction. And that is one of the quiet thrills waiting for us further in. And the third thing is why. Why did the sun go pale? Why for a whole year and not an afternoon? Why then, in that decade, and not some other? And this third question, the why, is the one that stayed locked and sealed for roughly 1,500 years. 15 centuries. Long enough that whole empires rose and fell in the not knowing. Long enough that the question itself nearly slipped out of the world's memory, became a curious line in an old book that scholars read and shrugged at and moved past. Who built it? When? And why? That is the shape of every good mystery, and here the answer to who and when and why was buried so deep, in places no human eye could reach, that it took the better part of 2,000 years and a kind of science nobody in Procopius's world could have dreamed of to pull it back into the light. Now let me widen the lens slowly, the way you might step back from a single window to see the whole dark shape of the house. Because it would be one thing if a single man in a single city had imagined a strange sky. The mind plays tricks. Grief and fear can paint the heavens any color you like. If all we had was Procopius alone, we might gently set his account aside as the exaggeration of a frightened age. But the dimming was not local. It was not the trouble of one town or one coastline. The pale sun hung over an enormous sweep of the world, over the whole northern half of the planet, as far as the records can reach. Over the eastern Mediterranean, where Procopius sat writing. Over Italy. Over the cold green island of Ireland on the far western edge of Europe. And, as we will hear in a while, over the rice fields and the dynastic courts of China on the very far side of the Eurasian landmass, thousands of miles east, where men who had never heard of Procopius and never would looked up at the same wrongness in the same sky and reached for their own brushes to write it down. That is the scale of the thing. Not a cloud, not a fog, not a single bad afternoon over a single bay. A veil drawn across the top of the world, hanging there for months on end, dimming the harvest light from Ireland to China in the same handful of years. Whatever did this was large enough, and high enough, and stubborn enough to stain the sky of an entire hemisphere and keep it stained while the seasons turned beneath it. And the people who lived under that veil had no instruments to measure it, no satellites to look down on it, no way at all to understand what was floating up there between them and their star. They only had the cold, the thin light, the failing crops, and the dread. So before we go further down, before we descend into the heart of it, let me do one small thing, the way one traveler might turn to another on a long, slow journey, and simply ask where they have come from. Wherever you are listening tonight, whatever the hour is where you are, whatever the weather is doing outside your own window, I would genuinely like to know. If you feel like leaving a single line in the comments to say where in the world you have settled in from, I read them, and there is something quietly lovely about a strange old story like this one being shared by people scattered all across the same planet that once went dark together. And if you are new here at Wisdom Docs and you would like more of these slow walks into the deep and the half-remembered, the kind of stories that ask nothing of you but to lie back and drift, then by all means, stay. Subscribe if it suits you. No rush. The tide will keep. Now. Let me make you a promise about where we are going, so that you can let go of any worry about following it, and simply sink. Here is the promise. The men and women who lived through that year are long gone. Their cities are dust or buried under newer cities. Their fields are someone else's fields now. The frightened farmers who watched the wheat fail under a pale sun left no diaries, no photographs, no measurements. Almost nothing but a few lines of horrified prose from the educated few, like Procopius, who could write. By every ordinary rule of history, the truth of what happened to that sky should have been lost completely, dissolved into legend beyond all recovery. A whisper, a rumor of a dark year long ago. And yet it was not lost, because there were witnesses to that year who could not write and did not need to. Witnesses who kept no diaries because their whole bodies were the diary. There were living things alive in 536 that recorded the cold in their own flesh, faithfully, automatically, the way you might lay down a ring on a tree. And there were other witnesses too, stranger ones, silent ones. Sheets and glaciers of ancient ice lying in the cold places of the world, quietly catching and freezing and storing a record of the very air that year, sealing it away layer by layer, like pages pressed in a book that no one would open for 1,000 years and more. That is the wonder I want to walk you slowly toward over these hours. The trees remembered, the ice remembered. They held the secret of that pale sun through every century that humans nearly forgot it. Through the fall of the Western Empire, through the long medieval centuries, through plagues and crusades and revolutions, through the entire span of the modern world, patiently keeping a record of one terrible year, until at last, in our own time, people learned how to read them. People learned to count the rings of a tree back across 2,000 years and put a finger on a single bad summer. People learned to drill into a glacier and lift out a core of ice and read the chemistry of an ancient sky. And when those silent witnesses were finally cross-examined and finally made to agree, they told us what Procopius could only dread. They told us what happened and when, and at last, and this is the part that took the longest of all, they told us why. But all of that is ahead of us. For now, stay here, in the strangeness of the dimming itself, because there is a second witness from that age I want you to hear, and his account is even more vivid than the first. His name was Cassiodorus. Magnus Aurelius Cassiodorus, to give him his full and stately name. He was not a soldier or a frightened farmer. He was a statesman, a high administrator, a man of letters who served the Ostrogothic court that ruled Italy in those years, a man whose whole working life was the careful drafting of official letters and decrees, the dry machinery of governance. He was, in other words, exactly the sort of measured, sober, unexcitable man you would want as a witness if you were trying to prove that something genuinely strange had occurred. Not a poet given to flights of dread, a bureaucrat, a man whose business was the plain and orderly running of the world. And even this man, this composed administrator, writing in a collection of his official correspondence known as the Variae in its 12th book, even Cassiodorus could not keep the alarm out of his words when he turned to the sky. He wrote of a sun of a bluish color. Sit with that for a moment, slowly. Not a pale sun merely, not a dimmed sun, but a sun gone blue. The color drained and shifted, the light cast over the land turned cold and strange and unfamiliar. The whole quality of daytime altered into something you would not recognize from any ordinary year of your life. He wrote of the moon, too, that it had been despoiled of its splendor, robbed of its brightness, the night sky as dulled and wrong as the day. And then he set down a line that catches at the heart of anyone who has ever watched a season fail to arrive the way it should. He wrote that the seasons themselves seemed all confused together, the reliable old wheel of the year, spring into summer, into autumn, into winter, the rhythm by which every farmer who ever lived had planted and reaped and survived, That wheel had come loose. The seasons were blurring into one another, none of them quite itself, none of them keeping faith with the calendar. He described a prolonged frost where there should have been no frost, an unseasonable drought. He wrote of crops ruined in the fields. And then he gave us a single sentence that once you have heard it, you do not easily forget. A sentence that contains the whole quiet horror of that year in a handful of plain words. He wrote that they had endured a winter without storms, a spring without mildness, and a summer without heat. Let those land one at a time, slowly, the way they would have landed on the people living it, a winter without storms. That might sound almost gentle, almost a mercy, until you understand that to a farmer it meant the ordinary turning of the weather had stopped, that the sky had gone flat and still and wrong, that even the violence of the season had been smothered under that veil. A spring without mildness. The season of return, the season when the cold finally breaks and the soil warms and the world leans back toward life, arriving with no softness in it, no thaw in its proper time. The promise of spring made and broken. And then, the cruelest of all, a summer without heat. The season the entire agricultural year is built around, the long warm months in which the grain swells and ripens and fills, in which a whole people lays down the food that will carry it through the dark half of the year. And that summer came without its heat. The sun that should have ripened the wheat hung pale and blue and useless overhead, and the grain did not fill, and the harvest did not come, and Cassiodorus, the careful administrator with his careful pen, wrote down that the crops were ruined, and surely understood, as he wrote it, exactly what a ruined harvest meant for the people who depended on it. Hunger. He was describing the doorway to hunger. Now hold these two men in your mind together side by side across the miles that separated them. Procopius in the Byzantine East by the Eastern Mediterranean, writing of a sun like the moon, a sun in a year-long eclipse, a most dread portent. Cassiodorus in Italy in the West, writing of a sun gone blue, of seasons confused together, of a summer with no heat in it. Two educated men, two different lands, two different languages, two completely separate accounts, set down independently, neither one copying the other. And both of them, in the same handful of years, describing the same impossible thing in the sky. The same pale, sickly, wrong sun, the same failure of warmth, the same dread. That, you see, is when a historian's ears prick up. One frightened account can be doubted. Two independent witnesses far apart agreeing on the strange and the specific. That is the beginning of evidence. That is the first faint scent on a very cold trail. And so we arrive, gently, at the question that will carry us forward into everything that follows, the first true open loop of our long night together. We have these words. We have Procopius and his sun like the moon. We have Cassiodorus and his bluish sun and his summer without heat. We have, scattered across the records of the world, a handful of educated men insisting that for a year or more the light itself went wrong. But here is the trouble, and it is a real and serious trouble, the kind that kept this mystery sealed for 15 centuries. How do you prove a dead man's account of the sky? Think about it honestly, the way a careful person would. Procopius and Cassiodorus were not scientists. They had no thermometers, no instruments, no way to measure the dimming they described, only their own frightened eyes and their own choice of words. And words can stretch, words can exaggerate. A bad year, lived through in fear, might swell in the telling into something larger and stranger than it really was. Perhaps the sun was only a little hazy, and the dread did the rest. Perhaps the bluish color was a single memorable evening that grew, in the retelling, into a whole pale year. Perhaps there was a local fog, a regional smoke, a season of bad weather that two anxious men each described in their own overheated way. People who lived a long time ago were not lying to us, but they were not measuring either. They were feeling, and feeling is not proof. And these were the careful witnesses, the ones who could write at all. Behind their few lines stood the vast silent mass of everyone else, the farmers, the herders, the children, the millions who lived under that pale sun and left not one written word behind. How could you ever recover the truth of what they endured? How could you ever stand at this distance, 1,000 years and more downstream, and say with any confidence, yes, the sky really did go dark, and here is precisely how dark, and here is the exact year, and here, at last, is the cause. The witnesses who could speak were too few and too prone to dread. The witnesses who suffered most could not speak at all. By every ordinary rule of how we know the past, the trail should have gone cold here, at these few haunted sentences, and stayed cold forever. For a very long time, that is exactly where it stayed, a curiosity. A strange dark passage in an old Byzantine book, and a stranger one in the letters of an Italian administrator. A year that something terrible seemed to have happened to the sun, and no way under heaven to prove what, or to be sure even of when. Scholars read the lines, they wondered, and, having no way to test the wondering, they moved on, and the pale sun of that year sank back into the deep waters of the forgotten, where so much of the ancient world has gone down and not come up. But it did come up. That is the promise I have made you, and that is where our slow descent is taking us. Because the answer to that impossible question, how do you prove a dead man's account of the sky, did not come from any library. It did not come from finding some new, lost manuscript, some fresh, frightened witness to add to the pile. The proof, when it finally came from somewhere no historian had thought to look for it. It came from the trees. It came from the ice. It came from the patient, silent, unwritten records kept by living wood and frozen water all across the northern half of the world. Records that were lying there, untouched and unread, the entire time that the question went unanswered, simply waiting for human beings to learn the language in which they were written. And so the next thing we have to understand before we can go any further down is how on earth a tree can remember a single bad summer 1,500 years after the fact. How a ring of wood, no wider than the width of a fingernail, can be pinned to one exact year and made to testify. How the cold of 536 was written into living things at the very moment it happened and held there faithfully through every one of the centuries since. So let the lamp burn low. Let your breath slow down to match the slow turning of all those years. We have heard the human witnesses now, the dread of Procopius, the blue sun and confused seasons of Cassiodorus, the year the warmth went out of the light across the top of the world. We have stood at the edge of the question that sealed the mystery for so long, and now we are going to step, quietly and without hurry, toward the silent witnesses who finally answered it, toward the rings inside the trees that were standing and growing and suffering in that very year, toward the cold archives of wood and ice that remembered a year the human world had very nearly let slip away forever. Stay with me. There is no need to reach the end tonight. The trees waited 15 centuries. We can afford to take our time. Begin then not with the trees themselves, but with the man who first heard them speak. Picture a year around the start of the last century in the dry, high country of the American Southwest, where an astronomer named Andrew Ellicott Douglas was puzzling over a question that had nothing, at first, to do with history. He was studying the sun. He wanted to know whether the great storms on its surface, the rhythm of sunspots waxing and waning, might leave some trace down here on the earth. And it occurred to him that if the sun governed the rain and the rain governed the trees, then the trees, year by year, might be quietly keeping a record of the weather no human hand had ever bothered to write down. A wet year, a fat ring; a dry year, a thin one. The wood was a ledger, and nobody had thought to read it. That is the seed of the whole thing. That is where the language was first learned. And though Douglas himself is not the man who solved 5 and 36, the method he founded is the only reason the question could ever be solved at all. And so it is worth sitting with the simple, almost unbearably patient idea at the heart of it. A tree in the cold, limited places of the world, high on a mountainside, far in the north, where the growing season is short and every degree of summer warmth is precious, lays down exactly 1 ring of new wood each year it is alive. In a kind summer, with warmth and rain enough, that ring is broad. In a cruel summer, when the cold comes early and the sun gives no heat, the tree can barely build any new wood at all, and the ring it manages is narrow, cramped, a thin dark line pressed in hard against the years on either side of it. And so a single terrible year leaves a single terrible mark. Not a vague impression, not a blurred decade. 1 ring for 1 year, narrow as a held breath. The tree does not interpret, it does not exaggerate or forget or copy down a rumor from a chronicle long since lost. It simply records faithfully, with no agenda at all, what the summer was actually like at the exact spot where it stood. This is what makes wood such an honest witness. And an honest witness is precisely what the case of 536 had been missing for 1400 years. Procopius could be doubted. A man writing of dread portents in a history of wars might lean toward drama. But a frost-scarred ring in a tree that was standing in that very summer has no interest in drama. It only has the truth of the cold. But here is the difficulty, and it is a real one, the kind of obstacle that kept this whole field honest in its early decades. A single ring on its own tells you almost nothing. You can cut a beam of ancient wood from a buried bog or an old roof timber and count its rings, 50 of them, 100, 200, and know that the tree lived that many years. But which years? Where, in the long river of time, does that little run of rings actually belong? A narrow ring near one end might be 5 and 36, or it might be 1536, or it might be some hard summer no one ever named at all. The wood remembers what the weather was. It does not by itself remember when. And so the half-asleep mind drifts toward the obvious question, the one that sounds for a moment like an objection. If a beam of dead wood cannot tell you its own dates, how could anyone ever pin a frost ring to one exact calendar year, 15 centuries gone? How do you turn a nameless run of narrow rings into a confident, specific 536, not the 530s, not roughly the 6th century, but that 1 year, the year of the dimmed sun, the year Procopius watched the light go pale? It seems, at first, like an impossible leap. It seems like the kind of precision the deep past should never allow. The answer is a quiet trick of overlap, and it is one of the most elegant ideas the human mind has ever turned on the problem of time. It is called cross-dating, and once you see it, you cannot unsee it. Begin with a living tree, one you can stand beside and touch, a tree whose outermost ring you know with certainty because it grew last summer and the one before it the summer before, and so on, backward into the dark of the tree's own beginning. From that living tree you have a run of rings anchored to real, named years, perhaps a few centuries deep. Now the wood remembers both what, and when. And inside that run of rings there is a pattern. A signature, fat year, thin year, thin year, fat year. A fingerprint of climate that the tree shared with every other tree growing near it in the same summers, all of them fed by the same rains and starved by the same droughts. So you take an older piece of wood, a dead one, a beam pulled from a bog or an ancient ruin, whose dates you do not yet know, and you look for that fingerprint. You slide its pattern of fat and thin against the pattern of the living tree, searching for the place where the two overlap, where the older wood's final decades match ring for ring, the living tree's earliest one. When you find that overlap and the match when it is right is unmistakable, a long stretch of years agreeing in every wide and narrow detail, you have just handed the dead wood a calendar. Its rings are no longer nameless. They are dated exactly by their handshake with a tree whose years were known. And then you do it again. The older wood now reaches further back than the living tree did, into years no living thing still records. So you find a piece older still, and overlap that with the wood you just dated, and again, beam to bog oak to buried timber, each one passing the calendar back to the next, like a torch carried down a long dark stair. Living trees clasp hands with dead ones, and dead ones with deader, until the chain of overlapping fingerprints runs back not centuries, but thousands of years, every single ring along the way pinned to its own exact summer. This is how a tree ring chronology is built, not by guessing, not by carbon estimates that wobble by decades, but by an unbroken sequence of matched patterns anchored at the near end to a tree someone could still walk up and lay a hand against. And this is why when such a chronology reaches a certain narrow, frost-scarred ring and the years are counted back along the chain, the cold of that ring does not arrive as the 530s or as roughly the 6th century or as some soft and arguable estimate. It arrives as a year. It arrives as 536, named and certain, because the calendar was carried back to it ring by faithful ring across all the centuries between. The tree was alive in that summer. It felt the sun fail. It built its meager scrap of wood and held the memory there, and the slow, patient work of overlapping fingerprints is what finally let us read the date stamped silently inside. So now we have the method in our hands, the simple, almost unbearable patience of it. We know a tree can remember one bad summer, and we know how that summer can be pinned to its true year. What we have not yet asked is what those trees actually said when scientists finally went looking for 536 inside them, whether the rings agreed with Procopius, whether the cold was written there as plainly as the dread was written in his ink. The answer, as it turns out, was recorded with a clarity that would have astonished the Byzantine historian himself. Mike Baillie came to the question of 536 not as a historian looking for confirmation, but as a scientist looking at patterns, and the patterns he found were sufficiently disturbing that he spent years trying to understand them. Baillie worked at Queen's University Belfast, and his instrument was the accumulated ring record of Irish bog oak, ancient trees that had fallen into the cold, oxygen-poor depths of Irish peat bogs and been preserved there for centuries, for millennia, their wood still holding the faithful record of every summer they had lived through. Bog oak is one of those materials that stops you for a moment when you understand what it represents. A tree that died perhaps 2,000 years ago, sank into the bog, was sealed away from the decay that claims everything else, and lay there in the dark while empires rose and fell above the surface until someone pulled it out and sliced into its rings, and the summers came out, counted and measurable, one by one. Baillie built chronologies from these trees. That slow, patient overlapping process of matching fingerprints across samples until the chain of rings ran backward without a gap. And in the record that emerged, certain years leapt out. Certain years were unmistakable, not because Baillie was looking for them, but because the trees could not have spoken more plainly if they had been asked to. The decade beginning in 536 showed some of the narrowest, most stunted rings in the entire 2,000-year record. Not the narrowest in a century, not the narrowest since some medieval cold spell that older readers might half remember. The narrowest growth sequence of 2 millennia. Rings so thin they represented barely any growth at all, summer after summer after summer, as though the trees had simply given up on the idea that warmth would return. Baillie described this as among the most severe environmental downturns visible in the tree ring archive. When you stand that claim against everything we know about the last 2,000 years of European climate, the medieval warm period, the Little Ice Age, the chill of the Maunder minimum when sunspots vanished and winters ground on, and still the 536 decade holds its terrible record, the weight of it becomes real. The trees did not lie. The trees had no reason to lie. They simply grew what the summer allowed, and in those years, the summers allowed almost nothing. Now, to understand why that registers as more than a historical curiosity, it helps to think carefully about what a tree ring actually is, and what it captures, and why a cold summer writes itself into wood in the way it does. A tree in a cold, limited environment, one growing near a glacier, or near the timberline on a high mountain, or at the edge of a subarctic forest, lives at the very margin of the possible. It grows only in summer and only when temperatures are warm enough to drive the chemistry of wood formation. In a good summer, cells divide, new wood is laid down, and the ring that results is wide and dense. In a bad summer, and a summer shortened by cold or cut through by a killing frost, the tree forms less wood, and the ring it leaves is thin. Sometimes, if a frost comes hard during the growing season itself, the tree does not merely slow down but is injured at the cellular level, and the ring it forms carries a visible scar, a band of distorted, damaged cells that researchers call a frost ring, or sometimes a light ring, because when the wood is sliced thin and held against a light source, the ring glows differently from the rest. It has the look of something hurt. Think of it like this: if you have ever seen what happens to a young plant when the temperature drops sharply in what was supposed to be a spring night. The leaves curl, the tender green growth goes pale or black, the damage is written plainly in the tissue. Then you have some sense of what a frost ring records. A tree does not die from one bad frost, not usually, but it carries the wound inside its wood for the rest of its life. Centuries later, when someone takes a core sample from that tree, or in the case of bog oak, when someone cuts into a trunk that has been lying in a peat bog for 2,000 years, that old wound is still there, still readable, still pointing to the summer when the cold came. This is the alphabet in which the catastrophe of 536 is written. High-altitude trees are the most sensitive recorders precisely because they live closest to the edge. A bristle-cone pine at 11,000 feet on a ridge in the American West has almost no thermal margin. A degree or two of summer cooling is the difference between a reasonable growing season and a season so short the tree barely manages to form a ring at all. The same is true of a pine or larch growing near the timberline in the Alps, or a spruce near the boundary of the boreal forest in Scandinavia. These trees are living thermometers. They have been recording the temperature of Northern Hemisphere summers for thousands of years, steadily and without comment, building their narrow archives of wood while the humans below them came and went. And across those high-altitude, high-latitude archives, whether in Ireland's bog oaks, or in the mountain forests of Europe, or in a very specific grove of ancient trees growing on ridgelines in the American West, the decade of 536 leaves the same mark. The American connection is worth pausing on because it carries a particular kind of weight. The same decade of cold that Cassiodorus felt in Italy, that Procopius recorded in Constantinople, that the Chinese dynastic histories noted in frost and famine, is also recorded in trees that were alive in California and Nevada during the same years. Trees so ancient that some of them are still alive today. These are the bristlecone pines, gnarled, wind-twisted, impossibly old, growing in the dry, rocky heights of the White Mountains and the Great Basin, some of them among the oldest living organisms on the planet. Two researchers, Valmore Lamarche and Catherine Hirschberg, did the painstaking work of looking at these trees and asking what they could say about major volcanic events in the past. Because by the 1980s, when their work appeared, the connection between large volcanic eruptions and sudden cold snaps was well established in principle, and it was known that frost rings in bristlecone pines tended to cluster around years when the historical or ice core record suggested an eruption had happened. Lamarche and Hirschberg identified frost rings in these California trees that correlated with known volcanic years, and in the ring pattern from the 6th century, the signature was there. The same period that left narrow, stunted rings in Irish bog oak left its injury inside trees growing on ridges in the American West, 5,000 miles away, under a different sky but the same dimmed sun. That is what it means to say the catastrophe was recorded on two continents. The same light failure, the same cold, the same volcanic veil stretched across the stratosphere above the Northern Hemisphere, pressing down on the growing seasons of trees that would never know each other, would never have any connection except the shared experience of a summer that came to nothing. It is a strange kind of solidarity, that of trees. But the rings by themselves, even with that twin testimony from opposite ends of the Northern Hemisphere, still leave an important question unanswered. They say there was cold. They say the cold was severe and prolonged, and among the worst in 2,000 years. They do not by themselves explain the mechanism. They do not say why the summer of 536 produced almost no heat. For that, you need to know something about what the rings are actually measuring, and you need to understand what sits between the sun and the surface of the Earth, and what can interrupt the connection between them. A tree ring records temperature. More precisely, it records the warmth available during the growing season, the accumulated thermal budget of a particular summer. But what determines summer temperature? For a tree growing in the 6th century, long before industrial emissions, the answer is primarily the sun and the atmosphere between the sun and the tree. And the atmosphere, it turns out, can be loaded with material that changes everything. When a volcano erupts with sufficient violence to punch its plume of gas and ash high into the stratosphere, not just into the lower atmosphere where weather moves, but into the cold, still air, 15 or 20 kilometers above the surface, where nothing washes things clean, it injects enormous quantities of sulfur dioxide. And that sulfur dioxide, once in the stratosphere, reacts with water vapor to form tiny droplets of sulfuric acid, which spread across the globe in the stratospheric winds and linger there, sometimes for years, forming what researchers call a stratospheric sulfate aerosol layer, or, in plainer language, a dust veil. The dust veil does something simple and devastating. It reflects sunlight back into space before it reaches the surface. Not all of it. The sun does not go out entirely, but enough. Enough to reduce the solar energy reaching the ground by a few percent. Enough to shift the thermal budget of a summer by a degree or two. Enough, in other words, to write itself into tree rings. And here is the crucial part of the mechanism, the part that makes the story scientific rather than merely metaphorical. The same sulfate that forms the aerosol veil and drifts around the stratosphere eventually falls out of the atmosphere, as it always must. What goes up must come down, and when the sulfate from a volcanic eruption falls out of the stratosphere at the poles, it lands on the ice and is buried. Year by year, the snowfall of each successive year pressing the previous layers deeper, building a compressed archive of atmospheric chemistry that goes back hundreds of thousands of years. Polar ice cores are not quite tree rings, but they are doing something analogous in their own medium, at their own pace. Where a tree says the summer of a given year was warm or cold, an ice core says a volcanic eruption deposited sulfate into the atmosphere in a given year. Both records are annual, both are physical rather than documentary, and both are silent. They say what they say, not because anyone asked them to, but because chemistry is chemistry and physics is physics, and the world does not forget, even when no one is watching. When scientists drill a long column of ice from a glacier that has been accumulating snow for centuries and examine it layer by layer for chemistry, and when they find a sudden spike in sulfate concentration at a particular depth, a spike far beyond anything natural background variation would produce, they are reading the record of an eruption. The ice has the date because the layers above and below can be counted. The ice has the chemistry because the sulfate is measurable and characteristic. And if there are also, frozen within that same layer, microscopic fragments of volcanic glass, actual physical material from the volcano itself, carried by the eruption cloud and deposited alongside the sulfate, then the ice holds something even more specific. It holds the fingerprint of the eruption in a forensic sense, glass that formed inside a particular volcano with a particular chemical composition that cannot be mistaken for glass from somewhere else. This is what the researchers meant by tephra. It is the volcanic glass, and it is what the ice core from the Colle Gnifetti glacier in the Swiss and Italian Alps was eventually found to contain, from a layer corresponding to the early part of 536, frozen there since that same winter when the snow fell and covered whatever the wind had carried south from the north, pressed and preserved under every subsequent season's snow until a drill came down and pulled it out 14 centuries later in tiny glass shards no wider than a strand of human hair. Before we reach that moment, because it is worth approaching it carefully, since it is the moment the case turns from well-supported hypothesis to something approaching proof, it is worth staying with the human experience of what the trees had recorded for just a little longer, because there is another set of witnesses less studied than Procopius and Cassiodorus who tell a version of the story from the far end of Eurasia, and whose accounts serve as a kind of confirmation that the dimming was not a regional European affair, but something planetary in scale. Michael the Syrian was not a contemporary of the events. He was a 12th century patriarch who compiled earlier, now largely lost, sources into a chronicle of Syriac church history, and the portions of his text that deal with the 6th century draw on accounts written much closer in time to the events themselves. The number he records, that the sun was darkened for 18 months and shone for only some 4 hours a day during that time with a feeble, blue-tinged light, has the character of a second-hand or third-hand transmission rather than an eyewitness report, and it must be held with appropriate care. An 18-month dimming is not impossible, given what we now understand about prolonged stratospheric aerosol loading, but the precision of the figure and the chain of transmission through which it reached Michael the Syrian mean it cannot be read with the same confidence as Procopius's direct contemporary account. What it does, rather, is add a voice from a different tradition, a different geographic and cultural context that is nevertheless describing the same phenomenon. A sky that withheld its light for far longer than any natural darkness ought to last. And then there are the Chinese records. From the Chinese dynastic histories, the Nanshe and related compilations that preserve the administrative and climatic observations of the era, come entries describing extraordinary cold and agricultural failure in the same general period. Descriptions of yellow dust that fell from the sky like snow, of frost and snowfall arriving in summer, of crops that failed and livestock that perished, and populations that went hungry. The precise phrasing and the precise dates require care in translation and in transmission, as dynastic histories were written and revised over long periods, but the essential content, cold arriving in summer, famine following, something strange in the sky, is there in the record, offering from the eastern edge of Eurasia the same testimony that Cassiodorus was offering from the western edge. Yellow dust like snow. That phrase, if you think about it for a moment, is more specific than it might first appear. It is not merely recording that the sky was grey or the sun dim. It is recording that something was falling from the atmosphere. Particles, material carried by the wind from somewhere, and that this material was pale and fine, like snow, but was not snow. It was dust. Volcanic ash and aerosol particles transported by stratospheric circulation across the breadth of Asia, settling on the fields and rooftops of 6th century China as a pale, powdery reminder that the same event, whatever it was, had reached this far too. The corroboration spans the planet. A Byzantine historian in Constantinople, an Italian administrator at the Ostrogothic court, a Syriac chronicler drawing on older accounts, Chinese imperial record keepers noting unusual cold and skyfall, and, speaking their slower language, the trees of Ireland, of the Swiss Alps, of the American Great Basin, all growing their miserable thin rings in the same years, all carrying their frost-scarred wounds from the same cold summers. Every archive says the same thing, in its own medium, in its own language, across thousands of miles of separation. Something went very wrong with the sky in 536, and the cold that followed did not lift quickly. Now comes the number that turns the descriptive record into something measurable. When paleoclimatologists attempt to reconstruct the actual temperature during the years around 536, the figure they arrive at, from the combined evidence of multiple tree ring chronologies, calibrated carefully against the instrumental record where the two overlap and tested against independent proxies, points to a Northern Hemisphere summer cooling in the affected years of somewhere between 1.5 and 2.5 degrees Celsius. That range reflects genuine uncertainty, variation across regions and proxy types. The true figure was likely somewhere inside it. 1.5 degrees, 2 degrees, 2.5. Written plainly, these sound like small numbers. They sound like the kind of difference you might not notice stepping outside, the difference between a comfortable afternoon and a slightly cool one, the difference between light jacket weather and heavy jacket weather. They do not sound like catastrophe. But think about what agriculture was in the 6th century, and what a degree or two of summer cooling actually means in practical terms for someone trying to grow food. Grain crops, wheat, barley, rye, the staples on which early medieval populations depended, have effective growing seasons defined by temperature. When temperatures fall below a certain threshold, grain stops accumulating the calories and starch that make it harvestable. The growing season is not a fixed length on the calendar. It is a length defined by warmth. A summer that is 1.5 degrees cooler than average does not simply produce slightly less food. It produces a growing season that may be shortened by several weeks because the threshold temperatures are reached later in spring and abandoned earlier in autumn. And a growing season shortened by several weeks for a grain crop is often the difference between a harvest and no harvest at all. In Northern Europe, in the cooler and wetter regions where the margin was already narrow, in Ireland, in Northern Britain, in Scandinavia, in the upland regions of Central Europe, even small shifts in mean summer temperature could push subsistence farmers from marginal harvests into no harvest. The frost that comes 2 weeks earlier than expected in September destroys what the late-arriving warmth of June and July had just managed to start. The killing frost that falls in May before the grain has finished establishing wipes out what was planted in hope. A fraction of a degree is the difference between a harvest and starvation. This is not a rhetorical exaggeration. It is a reflection of how little thermal margin 6th century farmers had to work with in the higher latitude, higher altitude regions of the Northern Hemisphere, which are precisely the regions where the volcanic cooling of 536 and the following years would have hit hardest. The trees recorded the cold in their rings. The Chinese chronicles recorded the frost in their summers. Cassiodorus recorded the absence of heat in the Italian seasons. And, somewhere between all of these records, in the silences between the written words, in the failed harvests that did not get written down because the people who would have written them were too hungry or too dead, is the lived reality of what those tree rings mean at ground level. A field in Ireland in the summer of 537, say, where the sky was still pale and feeble and wrong, where the grain came up late and thin, where the early frosts came before the harvest was ready, where the farmer looked at what the field had given and understood that it was not enough, that the winter ahead would be harder than any winter in living memory, that there was no surplus to draw on because the previous year had been no better. The rings do not record that farmer, they record only the cold, but the cold and the farmer are part of the same moment, the same reality, and the tree that grew in that same field, if there had been a suitable tree, a cold-limited one, growing nearby, would have added one more narrow ring to its record, one more piece of physical evidence pointing to the same year of suffering. The tree and the farmer, both witnesses. The farmer forgotten. The tree surviving, in a bog perhaps, or pressed into a building that was eventually excavated, waiting for someone to ask what summer felt like in the year that Procopius recorded the dying of the sun. Mike Baillie's work with the Irish bog oaks and the parallel evidence from European Alpine chronologies and from the bristlecone pines of the American West established beyond reasonable doubt that the 530s and early 540s were the worst period for summer temperatures in 2,000 years of the Northern Hemisphere record. Not the worst period in some local or regional sense. The worst in the entire span of time for which tree ring climate reconstruction has been built. A span that includes the depths of the Little Ice Age in the 17th century, that includes the Maunder Minimum, that includes other volcanic winters and cold spells and climate disruptions of various kinds. Nothing in 2,000 years was worse. That conclusion was already extraordinary when it emerged from the dendrochronological record. It was enough to confirm, in physical rather than merely anecdotal terms, that Procopius and Cassiodorus and Michael the Syrian and the Chinese chroniclers were not exaggerating, were not writing from political motives or narrative convenience or superstition, but were recording, as accurately as their medium allowed, a genuine atmospheric catastrophe whose traces are permanently encoded in the wood of trees that lived through the same years. But it still left the central question open. The rings could tell you that the summers were cold. They could not tell you why. They could not name the mechanism. They could not say whether it was a volcanic eruption or some other cause, a dimming of the sun itself perhaps, as some had theorized, or some other atmospheric phenomenon. To close that loop, to name the mechanism with the confidence the forensic metaphor implies, required a different kind of archive altogether. It required the ice, and getting to the ice, getting to the specific moment in 2018 when a team of researchers finally held in their hands the physical evidence that named the source, requires understanding not just what ice cores are and what they contain, but also a particular complication that had, for decades, kept the ice core story and the tree ring story from aligning in the way that scientists needed them to align. The problem was time. Not the passage of time in any romantic sense, not the difficulty of reaching back 14 centuries. The problem was more technical and more interesting than that, and it is the kind of problem that science has a particular way of facing, which is to keep asking the same question until the answer improves. Both tree rings and ice cores produce annual records. 1 ring per year, 1 layer of snow per year. But the process of counting those rings and layers backward from the present is not a simple matter of arithmetic. It involves matching patterns, making decisions about layers that are unclear or compressed or disturbed, and building a chronology that may have small accumulated errors that compound over time. Two different archives built by two different teams using two different methods and two different materials might both be accurate in their counting from the present back to, say, the 10th century and still have their 0 points, their absolute dates, offset from each other by a few years because the small ambiguities in each record accumulated differently. In the case of the 536 evidence, this kind of offset was a real problem. The ice core chronologies that existed before 2018 showed a large volcanic sulfate signal, the spike of eruption-deposited sulfate that you would expect if a major eruption had occurred. But the signal fell in a year that did not match 536 when the core was counted from the top. It fell a few years off, and a few years off is not close enough in a case where you are trying to demonstrate that the volcanic signal, the tree ring cold, and the documentary record of dimming are all pointing to exactly the same moment. If the sulfate spike is in 534, not 536, it might be a coincidence, not a cause. If it is in 538, it might have come after the dimming started, not before it. A few years is an enormous gap when you are trying to prove a causal connection between an eruption and a specific documented event. For a long time, this offset was a genuine obstacle to the convergence of the three archives. The trees said one thing about the date. The ice cores, as they were counted, said something slightly different. And the gap between them was enough to leave the story incomplete. Suggestive, compelling, but not quite closed. The resolution of that problem, the correction that finally brought the three archives into alignment, came from exactly the kind of unglamorous, painstaking, methodological work that gets done largely out of the public eye and whose importance becomes clear only afterward when the implications of the corrected chronology suddenly snap into focus. And when that alignment finally happened, when the ice core dates were corrected and the sulfate spike from 536 moved to exactly the year it needed to be, the three archives stopped telling slightly different stories and started telling one. The question of how ice core chronologies go wrong is worth sitting with for a moment, because understanding the error is what makes the correction so satisfying, and because it illuminates something important about how science actually works across centuries of frozen time. An ice core is read from the top down the way you might read a book, from the last page backward toward the first. The surface is this year, the ice just below it is last year, and so on backward through decades and centuries and millennia, each annual layer compressed by the weight of everything above it, growing thinner and harder to distinguish as you descend. In the upper portions of a core where the ice is recent and relatively uncompressed, the annual layers are thick enough to see and count with confidence. In the older portions, deeper down, the layers thin to translucent slivers a few millimeters thick or less, and even the most experienced glaciologist can miscount by a layer here and a layer there without being aware of it. Those small miscounts accumulate. A missed layer in the 3rd century adds 1 year of error to everything below it. A double-counted layer in the 5th century adds another. By the time you reach the 6th century, 1400 years below the surface, a small, steady accumulation of counting errors can place a given volcanic event several years away from its true calendar position. The sulfate spike is real. The volcano happened. But the date assigned to it by counting down from the top of the core carries the compound error of every ambiguous layer between the surface and that depth. This is not a flaw in the method so much as an honest limitation of it, and the scientists working with ice cores have always known it was there. The question was how to correct it, how to pin the core to a reliable external calendar anchor so that the accumulated counting error could be measured and removed. The answer, when it came, drew on the same logic that makes dendrochronology so powerful. Just as tree ring chronologists build their calendar by overlapping patterns from living trees back through dead timber and ancient wood, anchoring each ring to an exact year, ice core scientists looked for events they could date precisely from outside the ice. Events whose date was known independently from documentary sources or from other physical archives, and whose signature would appear clearly in the core as a distinctive chemical layer. Certain volcanic eruptions whose dates are fixed by historical record leave sulfate spikes in the ice that can serve as these anchor points. If you know from a medieval chronicle or from a dated lava flow that a particular eruption occurred in a particular year, and you can identify that eruption's sulfate spike in the core, you can check whether your count from the top matches the known date. If it is off by 2 years, you adjust. If it is off by 3, you adjust by 3. And once you have made that correction at one anchor point, the dates of everything above and below it shift accordingly. The work that Michael Sigl and his colleagues undertook over years of careful analysis was precisely this kind of anchor calibration, matching known eruptions to their ice core signatures, testing the count at each anchor, and systematically removing the accumulated errors that had built up across centuries of painstaking but imperfect layer counting. It is the kind of work that produces no dramatic discovery in itself, no single moment of revelation, but whose ultimate effect is transformative, because when the calibration is done carefully enough, what emerges is a corrected chronology in which events that had seemed slightly misaligned suddenly line up with a precision that was not previously possible. And that is exactly what happened with the 6th century. When the corrected ice core chronology was applied to the sulfate record, the large volcanic signal that had been assigned to a year a few years off from 536 moved, not by much, in absolute terms, a few years. But those few years were the difference between a coincidence and a cause, between a suggestive parallel and a forensic match. The spike, correctly dated, fell in early 536. It fell in the same year that Procopius looked up at a sun that gave light without warmth, like the moon, and called it a most dread portent. It fell in the same year that the trees at the edge of their cold tolerance, the ancient larches in the Alps, the bog oaks of Ireland, the bristlecone pines watching the high western deserts of North America, laid down their narrowest, coldest growth of the past 2,000 years. 3 archives, 3 different materials, 3 different methods, 3 different corners of the planet. And when the counting error in the ice was corrected, they agreed on the same year. That convergence, the moment when the independent witnesses finally stopped contradicting each other and spoke in unison, is the closest thing this story has to a solved case. It is not dramatic in the way a courtroom verdict is dramatic, because it happened not in a single afternoon, but over years of methodological revision, and the revelation came not as a single published paper's conclusion, but as the slowly dawning recognition that the corrected chronology fit together in a way the old one never had. But the intellectual weight of it is enormous. 3 separate physical records laid down by 3 completely independent processes, the quill of a Byzantine historian, the growth of a living tree, the slow settling of sulfate crystals from the stratosphere onto a glacier, were all, in the end, recording the same event in the same year. And the event was large enough to leave its mark on all 3 simultaneously. This is the part of the story that most popular accounts move past too quickly, because the method is less viscerally compelling than the drama of a dimmed sun or a dying city. But the method is the heart of it. Without the convergence, 536 remains an interesting historical curiosity. A year when a Byzantine historian happened to notice the sun looked strange, possibly for reasons we can only guess. With the convergence, it becomes something else entirely, a year whose catastrophe is written into the physical fabric of the planet, recoverable by science nearly 15 centuries later, as legible to a trained eye as the ink Procopius pressed on to vellum. Now it is worth understanding in some concrete detail what actually happened in the ice. The Colle Gnifetti glacier sits high in the Swiss Alps, at nearly 4,500 meters above sea level, near the summit of a peak called Monte Rosa on the border between Switzerland and Italy. At that altitude, temperatures remain below freezing even in summer, which means the snow that falls there does not melt and refreeze in the complicated way that confuses the layering in lower altitude glaciers. Each year's snowfall is sealed by the next year's snowfall and slowly compressed into ice, the layers preserved in sequence with remarkable fidelity. The glacier is, in this sense, an exceptionally clean archive, a place where the atmosphere's chemistry has been collected and stored year by year for thousands of years with relatively little of the distortion that affects other glacial records. The ice core drilled from Colle Gnifetti and analysed in the work that Michael Sigl and Michael McCormick brought to completion by 2018 was examined using a laser technique that allowed sampling at a resolution of 50 microns, about half the width of a human hair, fine enough to resolve individual annual layers and even the seasonal variations within a single year's ice. That level of resolution is not standard. It represents the kind of precision instrument work that becomes possible only when the scientific question is specific and important enough to justify the effort, and when the laboratory infrastructure exists to support it. Paul Mayowski and the team at the Climate Change Institute at the University of Maine supplied that infrastructure, years of careful analysis, sample by sample, working backward through centuries of compressed ice. At that resolution, the chemistry of the ice tells a detailed story. In a normal year, the record is relatively quiet. Background concentrations of various compounds, the usual faint chemical signatures of a world going about its business. In a year when a major volcano erupts and injects sulfur dioxide into the stratosphere, the record changes sharply. The sulfur dioxide converts through a series of chemical reactions with water vapor and oxygen into tiny droplets of sulfuric acid suspended in the stratosphere at altitudes of 15 to 30 kilometers. From there, winds carry them around the globe, forming a veil of aerosol that can persist for months to years, depending on the eruption size and the altitude at which the material was injected. This is the veil, the dust veil, as it is sometimes called in the historical and scientific literature, though sulfate aerosol is technically the more precise term. It does not block sunlight the way a thick cloud does. Instead, it scatters it, diffracting the light at wavelengths that strip out the warm red and orange frequencies and let through the cooler blues. The sun is still visible. There are no clouds. But the light is wrong. Pale, flat, bluish, robbed of its warmth and its directional strength. Procopius wrote of beams that were not clear. Cassiodorus described a sun of a bluish color and seasons seemingly all confused together. What they were both describing, without any framework to understand it, was the optical effect of a stratospheric sulfate aerosol veil, sunlight passing through a thin, planet-spanning chemical haze and arriving at the surface diminished, blue-shifted, and cold. The aerosol veil eventually settles. Stratospheric particles, fine as they are, slowly migrate downward and are carried by winds and precipitation onto the surfaces below, including onto the surfaces of glaciers. The sulfate that fell on Colle Gnifetti in 536 and the years following was not a large amount in absolute terms. You would not have seen it, you would not have tasted it. But it was measurably different from the background, and at 50 micron resolution, in the hands of a well-calibrated mass spectrometer, it was detectable. A clear chemical anomaly in a layer of ice that, according to the corrected chronology, corresponded to early 536. That sulfate signal alone would have been significant. It would have confirmed a major volcanic eruption, positioned the eruption in the right year, and provided a mechanism for the dimming that Procopius and Cassiodorus described. but it would not have told you where the volcano was. Sulfate is sulfate. The chemistry of the acid molecules does not carry a return address. The tephra did. Tephra is the collective term for the solid particles that volcanoes eject, the fragments of rock and glass that are blasted into the atmosphere and carried by wind before settling onto the surfaces below. In a large eruption, some of this material is fine enough to travel enormous distances across continents, across oceans, before eventually falling. And unlike sulfate, tephra has a chemical fingerprint. The composition of volcanic glass, its ratios of silicon, aluminum, iron, magnesium, calcium, sodium, potassium, and other elements reflects the specific chemistry of the magma chamber from which it came. Different volcanoes produce glass with subtly different compositions. Different volcanic regions produce glass with distinct, recognizable signatures. A well-characterized sample of tephra can be matched, with reasonable confidence, to a specific volcanic region and sometimes to a specific eruption. The tephra shards recovered from the 536 layer of the Colle Gnifetti core were small, very small, no wider in some cases than a hair is wide. Microscopic fragments of volcanic glass, each one a tiny frozen relic of an explosion that had occurred more than 14 centuries earlier. They had traveled to the Alps from somewhere else, carried by stratospheric winds, and settled into the ice, where they had remained undisturbed until a laser-equipped laboratory in Maine coaxed them back into visibility. When those shards were analyzed, their elemental composition measured and compared against the growing global database of tephra geochemistry that volcanologists have assembled over decades of systematic sampling from ancient eruptions around the world. The match pointed to Iceland. Iceland sits on the mid-Atlantic ridge where two tectonic plates are slowly pulling apart and magma wells up through the gap. The volcanism there is prolific and distinctive. Icelandic lavas and their associated tephra have a chemical signature, a specific combination of elemental ratios that differs measurably from, say, the volcanoes of Italy or Indonesia or Central America. The glass found in the 536 layer of the Colle Gnifetti core matched that Icelandic signature. It was, as far as the geochemical evidence could determine, the fingerprint of a high-latitude Northern Hemisphere eruption in a region that was well positioned, given the circulation patterns of the stratosphere in the Northern Hemisphere, to send its aerosol veil southward and eastward across Europe and Asia. This is a significant piece of information. Volcanic eruptions have different climatological effects depending on where they occur. A high-latitude eruption, Iceland, Alaska, Kamchatka, distributes its aerosol primarily across the hemisphere in which it erupted. A tropical eruption, by contrast, can inject aerosol into both hemispheres simultaneously because the stratospheric circulation carries material both northward and southward from equatorial regions. This means that the source latitude of an eruption affects both the geographic pattern of its cooling effect and the strength of the signal recorded in ice cores from different parts of the world. An Icelandic eruption in 536 would primarily affect the Northern Hemisphere. This is consistent with the distribution of the documentary evidence. It is Byzantine historians, Chinese dynastic records, and Irish and European sources that describe the dimming of 536, not accounts from the Southern Hemisphere, where the evidence for a 536 cooling anomaly is weaker. It is consistent with the geographic pattern of the tree ring record, which shows the strongest cold signal in the Northern Hemisphere's cold-limited environments. And it is consistent with the physics of how a Northern Hemisphere eruption would propagate its effects across the world. The case by 2018 had the following architecture. A corrected ice core chronology, anchored by carefully verified eruption dates, placed a major sulfate signal in early 536. In that same layer, microscopic tephra shards carried the chemical fingerprint of Icelandic volcanism. The tree rings of Europe, the British Isles, and North America showed the onset of their sharpest cold decline beginning in 536 and extending through the following years. And Procopius, writing in the 540s or 550s about events he had observed directly, described a sun stripped of its warmth beginning in that same year. None of these four witnesses knew the others existed. Procopius had never heard of dendrochronology. The trees had no awareness of Byzantine historians. The glacier received its sulfate without any knowledge of the growth rings forming in the larches far below it. They were independent. They agreed. And that agreement across materials and methods and continents and centuries is what Harvard's Michael McCormick meant when he described the 20s and 18 results as the culmination of a forensic case that had been building for decades. It was McCormick who gave the year its now famous designation. Speaking to Science magazine in 2018, he said that 536 was the beginning of one of the worst periods to be alive, if not the worst year. That phrase, or "good the worst year," has since travelled widely, attached to the story in nearly every popular account. It is worth pausing on where it comes from because McCormick was not speaking loosely or reaching for a headline. He was a co-author of the research, a medieval historian who had spent his career studying the economic and demographic catastrophe of the late Roman world, and he was describing a considered judgment about the weight of converging evidence. He was not saying that no individual in 536 had a worse year than any individual today, or that no year in human prehistory produced greater suffering. He was saying something more specific, that the convergence of climate shock, famine, and subsequent plague across the most densely documented civilization of the 6th century made this decade, beginning with 536, as bad as any period for which we have both a continuous historical record and corroborating physical evidence. The statement is careful in exactly the ways that good historical judgment is careful, limited to what the evidence can actually support, open to revision, and specific about the domain in which it is making a claim. And it is the kind of statement that is easy to misunderstand as sensationalism unless you hold the whole of the evidence behind it. Because when you do hold the whole of the evidence, the Byzantine sun like the moon, the Irish bog oaks recording their narrowest rings in 2,000 years, the Alpine glacier preserving its microscopic splinters of Icelandic glass, the claim is not sensationalism at all. It is an accurate summary of what three independent witnesses, finally made to agree after centuries of silence, have to say. There is one more piece of the convergence that is worth naming here, both for its elegance and for its honesty, which is the matter of what the 2018 findings identified and what they deliberately did not identify. They identified the region. They identified Iceland. The chemistry of the tephra was clear on that point, and the match to Icelandic volcanism was not a tentative suggestion, but a positive geochemical result. They identified the year, early 536, with confidence that the corrected chronology would not have made possible before the recalibration work was complete. They identified the mechanism, an Icelandic high-latitude eruption injecting sulfur dioxide into the Northern Hemisphere stratosphere, creating the aerosol veil that Procopius and Cassiodorus described without understanding. And they identified the physical trace of that event, frozen in the ice of the Swiss Alps for nearly 15 centuries, recoverable by a laser sampling technique at 50-micron resolution in a laboratory in Maine. What they did not identify, what the evidence, even at this level of precision, cannot yet determine, is the specific volcano. Iceland has many volcanoes. Some of them are well known: Hekla, Katla, Elgja, the Great Fissure System of Laki, the recently famous Eyjafjallajökull. Others are less so. The geochemical fingerprint of the 536 tephra narrows the field to Iceland as a region, and it rules out many other volcanic provinces around the world. But within Iceland, the number of candidate volcanoes remains more than one, and the specific vent from which the 536 eruption issued has not been definitively named. This is not a failure of the science, it is an honest statement of where the evidence stops. The tephra database is large and still growing, and future work, either adding more well-characterized reference samples from Icelandic eruptions or recovering better preserved tephra from additional ice cores around the world, may eventually narrow the field further. But for now, the 536 eruption is identified by its effects and by its regional origin, not by a name on a map. The detective has identified the region of origin with confidence. The exact address remains unknown. That honest remaining unknown is part of what makes the scientific account of 536 more satisfying, not less, than a story that simply claimed to have solved everything. The power of the convergence lies precisely in its specificity, in the fact that what it asserts it can demonstrate and what it cannot demonstrate it does not assert. The tephra is Icelandic, the year is 536. The mechanism is stratospheric aerosol. Those are the claims the evidence can support, and they are formidable claims. Beyond them lies honest uncertainty, carefully labelled. McCormick, when asked about the unidentified volcano, did not treat the gap as an embarrassment. He treated it as an invitation, the kind of open question that makes science continue, that sends researchers back to ice cores and tephra databases and the slowly accumulating library of geochemical reference samples, looking for the additional piece of evidence that will narrow the field further. The case is closed enough to tell the story with confidence. It is not so closed that there is nothing left to do. And it is worth appreciating, as you hold all of this together, Procopius's pen, the frost-scarred rings in the living wood, the microscopic glass in the glacier, that the chain of inference connecting these things runs in both directions. The science illuminates the history, explaining what Procopius saw and why Cassiodorus's crops failed. But the history also validates the science, confirming that the physical record is not an artifact of the laboratory, but a trace of something that real people experienced, wrote about, and suffered through. Each archive makes the others more credible. Each one asks the others to explain themselves, and the result of that mutual interrogation, 14 centuries after the sun went pale and the harvests withered, is a story that no single archive could have told alone. There is something in that worth sitting with quietly, the idea that the record of a catastrophe long enough ago to be genuinely forgotten has been reconstructed, not from guesswork or legend, but from the patient, unglamorous work of counting rings and measuring ice and matching the chemistry of microscopic glass shards against a database of known eruptions. The trees were alive when the sky went wrong. They noted it, in the only language available to them, by growing narrowly and coldly through the summer that should have been warm. The glacier received the settling sulfate and the drifting tephra without comment and sealed them into its layers, adding ice above them year by year for 14 centuries. And Procopius wrote his careful, bewildered sentences about a sun that gave light without brightness, like the moon. None of them knew they were preserving evidence. They simply were, the tree being a tree, the glacier being a glacier, the historian being a historian, and doing what historians do when they see something strange in the world, which is write it down as precisely as they can. That the three of them, separated by continent and material, and every conceivable difference in the manner of their recording, should have been found to agree so closely. Once the counting error in the ice was corrected, once the chronologies were properly calibrated, once the laser resolution was fine enough to pull individual tephra shards from half a hair's width of ice, is one of the more quietly remarkable things about this story. The year is named, the mechanism is understood, the volcano's home is known, if not its address. And somewhere in the ice above the 536 layer, preserved in the same Colle Gnifetti core and in ice cores from Greenland and other polar archives, another set of sulfate spikes waits to complicate the story further. because the 536 eruption was not the last. It was not even, as the evidence now shows, the largest. And the worst of what followed for the people living through these decades was not simply the cold and the failed harvests of a single bad year. It was the accumulation of catastrophes that the initial eruption helped set in motion. The second eruption signature appears in the ice approximately 4 years after the first. Around 540, the sulfate record shows another large spike. The tree rings show the cold deepening rather than recovering. And somewhere, on the other side of the world, from Iceland, in a part of the planet that the late antique Mediterranean world knew almost nothing about, a different volcano had erupted or was about to erupt. One whose effects, unlike the first, would reach not only the Northern Hemisphere, but both hemispheres simultaneously. This is where the forensic story of 536 turns out to be larger and stranger than the name implies, because 536 was not in the end a single year's catastrophe. It was the opening movement of a climatic disaster that would play out across decades, driven by a sequence of eruptions that no one living through them could have known were related, and whose full extent would not be apparent to any single witness at any single moment. The trees knew. Growing year by year in their cold, limited forests, recording each summer's warmth or chill in the width of their rings, they registered not the spike of a single volcanic year, but the long, sustained suppression of summer warmth across a decade and more. And the ice kept the record of why, spike after spike in the sulfate record, each one marking another eruption adding its veil to the stratosphere, each one extending the period of cold and dislocation before the aerosol could finally thin and dissipate and let the sun's warmth return to normal. The late antique Little Ice Age, as Ulf Büntgen and his colleagues named it in their 2016 paper in Nature Geoscience, drawing on tree ring records from the Alpine mountains and the European Alps to construct a temperature reconstruction for the Northern Hemisphere, did not begin in 536 and end in 537. It began in 536 and persisted with varying intensity until approximately 1660 AD, more than a century of anomalous cold compressed into the tree rings of forests across 2 continents, anchored in the ice of glaciers from the Alps to Greenland. And the first eruption, the Icelandic one in early 536, was its trigger. Not its only cause, or the volcanic sequence that followed. The 540 eruption and the one around 547 would extend and deepen what the first had begun, but it was the match that lit the fire. And it was the year whose name has come to stand, in Michael McCormick's phrase, for the beginning of one of the worst periods in recorded human history. And so we come to the question that the ice cores and the tree rings together answered, but that took the longest to ask correctly, because the initial reading of the evidence, the first natural conclusion, was that 536 had been a catastrophe, a single terrible year from which the world eventually recovered, a volcanic winter, a bad decade perhaps, and then normalcy. The corrected reading is something stranger and more unsettling, not one eruption. 3. Within a span of roughly 11 years, and not 3 eruptions separated by long intervals of recovery, but 3 eruptions stacked so closely together that the atmosphere never had time to clear between them, the stratospheric aerosol from the first still thinning when the second eruption loaded it again, the second still casting its veil when the third arrived. The triple punch, some researchers call it, a sequence that turned what might have been a single bad decade into something that endured for generations. The sulfate record in the ice is unambiguous about this. The 536 spike is there, large and datable, and then around 540 another spike, significant, possibly larger in some readings, marking another major eruption whose aerosols spread through the stratosphere and suppressed Northern Hemisphere summers again just as they were beginning to recover. And then around 547 a third, each one resetting the cooling. each one extending the period of suppressed harvests, shortened growing seasons, confusion of the seasons that Cassiodorus had written about as though it was something inexplicable, a disorder in the heavens. He was not wrong that it was a disorder. He simply could not know it was volcanic in origin, or that it would continue not for 1 year, but for more than a century. This is the late antique Little Ice Age, the name Ulf Büntgen and his colleagues gave to the climatic interval that their 2016 paper in Nature Geoscience identified and dated. The paper drew on tree ring records from the Alpine mountains of Central Asia and the European Alps, two geographically separate regions, two independent archives, both registering the same sustained temperature anomaly, to reconstruct Northern Hemisphere summer temperatures across this period. What they found was not a spike and a recovery, it was a sustained depression of temperatures lasting, with varying intensity, from around 536 to approximately 1660 AD, more than a century. Think of what a century means in agricultural terms. A century is not a disaster followed by rebuilding. A century of anomalous cold, even modest cold, even the kind of cooling that seems small in absolute terms, a degree or two in the wrong direction at the wrong time of year, is a transformation of the conditions under which people farm, herd, migrate, and organize their societies. Growing seasons that are reliably shortened by weeks, frosts that arrive earlier in autumn and later in spring, the edge of cultivation, the latitude at which certain crops can reliably be grown, pushed southward. Fields that had fed communities for generations rendered unreliable, communities that had been stable becoming precarious, and precarious ones collapsing entirely. The Büntgen paper made a significant argument that this climatic shift, this late antique Little Ice Age, was not simply a backdrop to the social disruptions of the 6th and 7th centuries, but a contributing cause of them. The migration period, the political transformations of the late Roman world, the movements of peoples across Eurasia, all of these unfolded against the backdrop of a climate that was measurably more hostile to settled agriculture than it had been in the centuries before 536. Büntgen and his colleagues were careful to frame this as correlation, as plausible mechanism, not as simple causation. Climate does not write history by itself, but it sets the conditions within which human choices, conflicts, and adaptations play out, and conditions that have shifted by even a degree at the wrong season can reshape the range of options available to a farmer, a community, a state. The 540 eruption remains the most contested piece of the sequence. The 536 eruption has been geochemically fingerprinted as Icelandic in character. The tephra from the Colle Gnifetti core, those microscopic shards of volcanic glass, carry the chemical signature of high-latitude North Atlantic volcanism. But the 540 eruption sulfate spike in the ice cores presents a different profile in some analyses, suggesting a different source. And one of the candidates that has been proposed, argued over, and not yet conclusively resolved, is Ilopango, a caldera volcano in what is now El Salvador. Ilopango is not an obscure volcano. It is the site of one of the largest eruptions of the last several thousand years, an eruption whose deposits, called the Tierra Blanca Joven, are found across Central America and even in deep-sea sediment cores, and whose estimated volume dwarfs most historical eruptions. A tropical eruption of that magnitude would have lofted sulfur dioxide into the stratosphere in enormous quantities, and a tropical injection, as opposed to the high-latitude Icelandic one, would have spread aerosol across both hemispheres rather than preferentially cooling the northern one. The question of whether Ilopango's great eruption occurred around 540 AD rather than in some other century has been argued in the scientific literature for years. Some analyses of the ice core record and of the regional ash deposits support a mid-6th century date, Others place the eruption earlier, in the 5th century, or later. The question remains genuinely open. This is honest science, not a failure of science. The evidence is complex, the archives imperfect, and the researchers engaged are working at the edges of what can be resolved. What is not open is the existence of the 540 sulfate spike itself. Whatever eruption caused it, it is there in the ice. And it is followed by the 3rd spike, around 547. The sequence is real. Its geographic sources are partly known and partly debated. And the effect? A sustained, multi-eruption suppression of Northern Hemisphere temperatures across the better part of a century is recorded independently in the tree rings of the Alps, the Altai and the American West, and in the chronicles of writers from Constantinople to China who described each in their own idiom a world in which the sky was wrong and the harvests failed. The human aftermath of this sequence is not difficult to imagine because it does not need imagination. The records are there, scattered across the annals of every civilization that kept them in this period. Famine. Not the ordinary hunger of a bad harvest, but sustained, multi-year food crises of the kind that destroy not just crops, but the social structures built around them. The granaries that had fed cities emptying and not refilling. The trade routes along which grain normally moved disrupted by the collapse of the surpluses that made them possible. The communities at the margins of agricultural viability, the ones whose harvests were already thin in good years, pushed past the breaking point. From Ireland, where the annals record famine in these decades, to the Chinese dynastic histories that speak of summer frost and yellow dust falling like snow, of people dying in their fields, the evidence of human suffering converges from the far ends of the Eurasian landmass. And this convergence is itself significant. A local disaster can be dismissed as a regional accident, a localized failure of crops or weather, when the same period of crisis appears in records from Ireland and China, from Constantinople, and from the Syriac-speaking communities of what is now Syria and Iraq. The argument for a common climatic cause becomes very strong. The crisis was not local, it was the crisis of a hemisphere. Michael McCormick has done something unusual for a historian. He has used the ice cores not just for temperature signals, but as an economic archive. The Colle Gnifetti glacier does not only record volcanic sulfate, it records lead, and lead, in the ancient and medieval world, was a byproduct of silver smelting. The process by which silver ore was refined, which involved melting lead-silver alloys and driving off the lead as oxide, some of which made its way into the atmosphere and eventually into the ice. The amount of lead in the ice at any given time period is therefore a proxy for the level of metalworking activity in the economy's upwind of the glacier, a measure, however indirect, of economic activity. The lead record in the Colle Gnifetti core shows a collapse around 536, not a gentle decline but a sharp drop in atmospheric lead pollution, consistent with a significant contraction of the silver smelting industries that had operated continuously through the Roman period and into the early medieval centuries, and this collapse in lead pollution persists. The recovery, at the point at which lead levels in the ice begin to rise again, signaling renewed economic activity and metalworking, does not come until around 640 AD, more than a century after the initial disruption. Think about what that means in practical terms. The mines that had operated continuously for centuries, producing the silver that funded armies and courts and trade, went quiet. The workers who had smelted ore, the merchants who had traded the refined metal, the economies that had depended on the circulation of silver coin, all of this contracted, not because of a political decision, not because of a military defeat alone, but because the conditions that made complex economic activity possible, stable food supplies, predictable surpluses, the confidence that came from knowing a harvest would follow a planting, had been disrupted at the most fundamental level by a century of anomalous climate. And then, 5 years after the sky first went dark, something arrived that was worse than cold. The Plague of Justinian. Named for the emperor who reigned in Constantinople when it struck. Justinian Theodosius, who had spent decades attempting to reassemble the Roman Empire, reconquering North Africa from the Vandals, taking Italy back from the Ostrogoths, building the great church of Hagia Sophia that still stands in Istanbul today. A man of extraordinary ambition and energy, reigning over the most powerful state in the Western world at the time, a state that had already been weakened by years of crop failures and famine and the financial strain of constant warfare. And into this weakened world in 541 and 542 came Yersinia pestis. We know this name now, the bacterium's name, because ancient DNA extracted from skeletal remains of the 6th century has confirmed it. Burials from Bavaria, dated to the period of the Justinianic plague, have yielded bone and tooth material in which the genetic signature of Yersinia pestis, the same bacterium responsible for the Black Death of the 14th century, the same organism that killed perhaps a third of Europe's population in the 1340s, has been identified and sequenced. The lineage is confirmed this was not typhus, not smallpox, not some unnamed fever. This was bubonic plague, the first recorded pandemic of it, reaching the heartlands of the Mediterranean world for the first time in recorded history. Procopius, who was in Constantinople when the plague arrived in 542, wrote about it with the particular horror of an eyewitness who understood that what he was seeing was without precedent. He described the swellings in the groin and the armpit, the buboes, characteristic of bubonic plague, the swollen lymph nodes packed with bacteria, and the delirium that often accompanied the disease, and the speed with which it moved through a city already crowded with refugees from the wars and the famines of the preceding years. He described how the dead accumulated faster than the living could bury them, how bodies were left in houses because there was no one to carry them out, how the normal rituals of death and mourning became impossible to observe. He was a careful observer, and his account carries the weight of someone recording what he actually saw, not what he had been told. The scale of the mortality is genuinely disputed. Older accounts, drawing on the most dramatic passages of Procopius and other chroniclers, placed the death toll in the millions, sometimes reaching the claim that the plague killed a third to a half of the Eastern Roman Empire's population. These figures are almost certainly too high. More recent historical and paleodemographic work has argued for a significant but perhaps less catastrophic mortality, and the debate among specialists about the actual demographic impact of the Justinianic plague continues. What is not disputed is that it was devastating, that it returned in waves. This first pandemic of plague was not a single event, but a series of outbreaks across the Mediterranean world, spanning roughly 2 centuries. That it struck populations already weakened by years of famine, and that it left the Eastern Roman Empire, for all its survival, measurably smaller and less powerful than it had been at the beginning of Justinian's reign. The connection between the climate disruption that began in 536 and the Justinianic plague that erupted in 541 is one of the most discussed and most carefully hedged topics in this area of research. The mechanism is plausible. Populations weakened by years of inadequate nutrition are more vulnerable to infectious disease in general. Famine and plague have accompanied each other throughout recorded history. Cold and wet conditions can shift the ecology of the rodent populations that serve as reservoirs for plague bacteria and the flea populations that transmit them. Disrupted human populations, refugees, migrants, people displaced from their normal lives and communities by crop failure and famine may be more likely to encounter novel disease reservoirs. All of these are reasonable arguments, and researchers have made them carefully. But historians who have studied this period most closely are also careful to say that the chain of causation is not a simple one, and that treating the Justinianic plague as an automatic consequence of the 536 climate shock would be a mistake. Plague bacteria do not appear spontaneously from cold weather. The bacterium has a history and a geography of its own, and the question of where the Justinianic plague originated and how it traveled to Constantinople involves considerations that go well beyond the climate. What can be said is that the populations it struck had already been under extraordinary stress for years, and that stress almost certainly shaped how the disease moved and how severely communities were affected by it. What the ancient DNA evidence adds to this picture is something striking. The Yersinia pestis lineage identified in the 6th century Bavarian burials is genetically linked to the lineage that caused the Black Death 8 centuries later. This is not coincidence. It means that the same bacterial strain, the same organism in its essential genetic identity, was capable of causing pandemic mortality at 2 very different points in history, under very different social and ecological conditions. The Justinianic plague and the Black Death are not 2 separate diseases that happen to look similar. They are, in a deep biological sense, the same event in 2 different centuries. The bacterium persisted, the conditions for pandemic eventually reassembled, and it struck again. For the people living in the Roman Empire, in the Sassanid Persian Empire, in the kingdoms of Western Europe and the nomadic confederacies of the steppe, in the courts of the Chinese dynasties and the communities of the Syriac-speaking East, none of this was visible as a connected whole. What was visible was that the world had become harder, that the harvests were less reliable, that winters were colder and springs came later, that the grain that had always been there was sometimes not there, that neighbors were dying of a disease that swelled the lymph nodes and brought fever and sometimes hallucinations and very often death, that the familiar order of things, the rhythms of planting and harvest, the confidence that trade routes would be open and coins would be worth something and armies could be fed, had become uncertain in ways that no one could fully explain. And slowly, over generations, the world that had existed before 536 ceased to exist. Not in a single collapse, not in the kind of dramatic fall that makes for easy historical narrative, but in the slow transformation of societies under sustained stress. The late Roman world became the early medieval world. The great cities of the Mediterranean, Alexandria, Antioch, Carthage, Rome itself, shrank. The rural landscapes of Western Europe became less densely settled, more forested, less organized around the complex infrastructure of Roman agriculture and trade. The political entities that had seemed permanent became fragile and then became something else. New powers emerged in the space that the old ones left, bringing with them new languages, new religions, new ways of organizing land and labor, and loyalty. Scholars debate how much of this transformation is attributable to the climate shock of 536 and the late antique Little Ice Age, and how much to the political and military events of the period, and how much to the plague, and how much to longer-term processes that had been underway for centuries. The honest answer is that these forces did not operate independently of each other. A climate that suppressed harvests weakened states financially. States weakened financially were less able to field armies. Armies that could not be paid lost battles. Lost battles opened frontiers. And all of this played out against the backdrop of disease that killed both soldiers and the tax-paying farmers who funded them. The causes were multiple and interlocked, and assigning weights to them is as much an art as a science. But we know that 536 was when it began. Not because a historian decided to start the story there, but because 3 independent archives, a Byzantine administrator's letter, the growth rings of trees that were alive at the time, and microscopic shards of volcanic glass frozen in an Alpine glacier, all point to the same year as the beginning of something that lasted for more than a century. This is the thing worth sitting with in the quiet of wherever you are right now. The trees that were growing in the mountain forests of Switzerland and the Altai in 536 did not know they were living through a catastrophe. They did not know about Procopius or Cassiodorus or the dimmed sun over Constantinople. They only knew, in the way that trees know things, through the chemistry of their own cells and the length of their growing seasons, that the summers were colder. And they recorded that knowledge in the only way available to them. They grew less. They laid down a narrow ring, a frost ring in some cases, a visible scar in the wood, the signature of cells damaged by a freeze during the growing season, a wound that healed but left its mark. And then they kept growing. Through 5137 and 538 and 539 each year, adding another ring, another record of the summer's warmth or chill. Through the eruption of 540 and the eruption of 547, recording each new pulse of volcanic cooling in the narrowing of their annual growth. Through the famine years and the plague years, indifferent to everything except the length and warmth of the growing season. Through the slow centuries of the late antique Little Ice Age until the climate finally stabilized around 1660 and the rings began to widen again, and the long cold that had begun with an Icelandic eruption in early 536 finally, gradually, released its grip on the Northern Hemisphere. Some of those trees are still standing, most are not, of course. A tree that was alive in 536 and died naturally might survive in a cold, dry, oxygen-limited environment like a high-altitude bog or a glacial valley, its wood preserved not by human intention, but by accident of chemistry and climate. And it is from exactly these preserved samples, Irish bog oak, high-altitude alpine timber, the ancient bristlecone pines of the American West that live for millennia in their thin-aired mountain fastnesses, that the dendrochronological record is built. Living trees overlap with dead ones that overlap with ancient ones, ring patterns matched and cross-dated until the chronology extends back continuously for thousands of years. Each ring in that record is a year. Each year is a data point, and the data points from 536 onward tell a story that no human writer working alone could have told with the same precision. Because human writers die, their documents are copied, and copyists make errors, and fires destroy libraries, and political upheavals cause the destruction of records, and languages die and must be slowly reconstructed by scholars centuries later. The account of Michael the Syrian, with his 18 months of dimmed sun and 4 hours of feeble daily light, reaches us through a chain of transmission that introduces uncertainty at every link. The Chinese dynastic histories describe summer frost and yellow dust in ways that match the physical record, but were edited and compiled long after the events they describe. Even Procopius, careful and contemporary as he was writing history with a political purpose, selecting what to record and how to frame it. The trees have no politics, the ice has no agenda. They recorded what happened with the indifference of physics and biology, and they kept that record intact through 14 centuries of human history that have seen empires rise and fall, languages appear and disappear, and the entire edifice of modern science constructed from almost nothing. The Colle Gnifetti glacier in the Swiss Alps, at an altitude where the cold and dry conditions prevent the ice layers from melting and mixing, preserved the sulfate from a volcanic eruption in Iceland in early 536 in a layer that Paul Majewski's team at the Climate Change Institute at the University of Maine could find with a laser sampling system precise to 50 microns, finer than the diameter of a human hair, and analyze for volcanic glass chemistry and identify as Icelandic in origin. Think about the chain of events that made that possible. An Icelandic volcano erupts. The sulfur dioxide it ejects reaches the stratosphere and spreads globally. Some portion of the resulting sulfate aerosol is deposited on the Colle Gnifetti glacier. The ice accumulates layer by layer, year by year, and the sulfate is sealed into the archive. For 14 centuries, while the Roman Empire became medieval Europe, and medieval Europe became the modern world, that layer of ice sits undisturbed in the cold, preserving its evidence. And then in 2018, researchers drill a core from the glacier, carry it to a laboratory, run a laser along its length with sub-millimeter precision, and in the vaporized material from a layer corresponding to early 536, find microscopic shards of volcanic glass whose chemistry matches the signature of Icelandic volcanism. The volcano cannot be named. The geochemistry identifies the region, not the individual vent. But the fingerprint is there, frozen and preserved and readable. And at the same moment, in the tree ring record that Mike Baillie of Queen's University Belfast had spent his career constructing from Irish bog oak and European timber, the year 536 shows up as a frost ring, a narrow ring, the beginning of the worst cold sequence in 2,000 years of dendrochronological record. And in Procopius's History of the Wars, written in Constantinople in the 6th century, the sun shines like the moon for a whole year. 3 witnesses separated by thousands of kilometers and every conceptual gap that divides a 6th century Byzantine historian from a living tree from a glacier's chemistry. And they agree. This is what the title means by solved. Not that every question has been answered. The exact volcano that erupted in 536 has not been named and may never be named. The ice core evidence is good enough to identify Iceland as the source region, but Iceland has many volcanoes, and the specific vent that produced the eruption, whose aerosols dimmed the sun for a year, remains unknown. The source of the 540 eruption, whether Ilopango in El Salvador or some other candidate, is still being argued in the scientific literature, with evidence on multiple sides and no consensus yet reached. The death toll of the Justinianic plague remains genuinely disputed among historians, and the mechanisms linking the climate shock to the plague's emergence and spread are still being worked out. These are not failures of the investigation. They are the honest boundaries of what the evidence can tell us, and researchers in this field are careful to mark those boundaries clearly. What has been solved is the shape of what happened. The convergence of 3 archives on the same years, the same events, the same sequence of cause and effect. The volcanic eruption that loaded the stratosphere, the aerosol that dimmed the sun, the cold that followed, the famine that accompanied the cold, the plague that arrived into a world already weakened. The detective story has a solution, even if some details of the crime remain unclear. And the solution was only possible because in 2018 the ice core chronology was corrected. The dating offset that had misaligned the sulfate spikes with the tree rings by several critical years was identified and resolved, and suddenly the 3 archives snapped into agreement, the evidence from the ice and the rings and the texts all pointing to the same moments, the same eruptions, the same years. Michael McCormick called it the beginning of one of the worst periods to be alive, if not the worst year. He was right to qualify it the worst period, not just the worst year. Because the year 536, terrible as it was, the year of the dimmed sun and the confused seasons, the failed harvests and the beginning of the cold, was not the full story. It was the first chapter of a story that lasted more than a century, written by 3 eruptions and the chemistry of the stratosphere, and the slow resilience and slow collapse of societies under sustained environmental stress. And all of that was hidden in plain sight in the rings of trees and the layers of ice, waiting for the science to develop the techniques to read it and the wisdom to cross-check the archives against each other. The evidence was always there. It took patience and instrumentation and the willingness to go back and correct an error in the dating and the collaboration of historians and climatologists and ice core chemists and dendrochronologists, people who, in an earlier era of scholarship, might never have spoken to one another, to finally read it correctly. The trees remembered, the ice remembered, and in the end, working carefully and honestly with what the natural world had preserved, we remembered too. There is something in this that goes beyond the historical and the scientific. Somewhere in a cold, limited forest in the Alps or the Altai, a tree was growing in the spring of 536, when the sky began to change. It had no understanding of what was happening. It only grew following the chemistry of its own biology, responding to the temperature of the air around it and the length of the days. When the summer came cold and short, it grew a narrow ring. When a frost damaged its growing tissue, it left a scar. It had no way of knowing that it was creating a record. It had no way of knowing that 14 centuries later, its ring would be matched against other rings in a continuous chronology stretching back thousands of years, and that the width and character of the ring it was laying down in that cold summer would tell a scientist the exact year and the approximate severity of the catastrophe then in progress. That is what dendrochronology is at its deepest level, not just a technique for dating wood, a form of listening, a way of hearing what the natural world was recording while humans were busy surviving and suffering and trying to understand what was happening to their sky. The trees were not trying to help. They were simply growing as trees do, 1 year at a time, each ring a year, each year a data point, and together, in their overlapping and cross-dated chronologies, they built an archive that no human civilization intended or could have built deliberately, an archive that survived the fall of the empires that existed when they were growing. The ice is the same. The Colle Gnifetti glacier was not trying to preserve the evidence of a 6th century eruption. It was simply doing what glaciers do, accumulating, compressing, preserving under its own weight and cold the atmospheric chemistry of each passing year. The volcanic glass that ended up in the layer corresponding to early 536 was not placed there for a scientist to find. It arrived on the wind like dust, one microscopic shard among millions, and was buried under 14 centuries of subsequent accumulation. That it was there to be found when the drill went in and the laser sampled the core is not a miracle. It is the ordinary operation of physics, but the finding of it, the reading of it, the understanding of what it meant, that was a human achievement built from centuries of accumulated scientific knowledge and decades of patient methodological refinement. And so the mystery of the worst year in history is not, in the end, a mystery about the past. It is a mystery about how we know the past, about what kinds of witnesses survive the centuries and what techniques allow us to read them, about how a Byzantine historian's careful description of a sun that shone like the moon can be confirmed by the chemistry of a glacier on the other side of the continent and by the growth pattern of trees that were alive when he was writing, about the power and the limits of convergent evidence, what it means when 3 completely independent archives agree, and what it means that even in their agreement, some questions remain honestly open. The exact volcano, unnamed. The precise death toll of the plague, disputed. The degree to which the climate shock caused, rather than merely accompanied, the social transformations of the 6th and 7th centuries, still being argued and likely to continue to be argued because these are genuinely hard questions and the evidence genuinely underdetermines the answer. But the dimmed sun, the cold summers, the failed harvests, the triple eruption sequence, the late antique, little ice age, the plague, the economic collapse written in lead in the ice, these are known. And they are known because trees grow 1 ring at a time, and ice accumulates 1 year at a time, and the natural world keeps records that outlast the civilizations of the people who lived inside the events those records describe. You are drifting perhaps in the dark of wherever you are, and somewhere in a cold forest at high altitude, a tree is growing, slowly, in the thin air, adding another ring to a chronology that has been accumulating for centuries. It does not know about you. It does not know about the scientists who will someday read its rings or the questions those rings might help to answer. It is simply growing as trees have always grown, 1 year at a time, 1 ring at a time, each ring a small, faithful record of the summer that made it. The year 536 is in there, somewhere, in the oldest of those trees and in the preserved timbers of trees long dead, a narrow ring, a frost scar, a year the tree survived and recorded and carried forward. And that single ring, matched against 1,000 others, helped to close a case that had been open for 14 centuries, to give a name and a cause to the dimming of the sun that a historian in Constantinople wrote about as a most dread portent, not knowing that what he was describing was the beginning of the worst century in the history of his world. The sky is clear tonight. The stars, if you can see them, are the same stars that Procopius could see when the dust veil finally thinned and the sun's light returned to its normal brightness. The cold has lifted. The rings in the wood are widening again. Tie off here at the Wisdom Dock. The tide will wait till morning.